record. Now you can see the screen as well, right? And you already have this PDF. So we will continue our discrete probability distribution. And today, last time we have learned about binomial distribution, right? In today's lecture, we will continue the discrete probability distribution. Last lesson, we have learned about Bernoulli as well as binomial distribution, right? What is Bernoulli distribution? When we have like only two outcomes. Yeah, when we have only two outcomes, that's success and failure. Yeah, that's a success and failure. We call P1 minus P as well as Q. Right, and this is P, and whereas Q is 1 minus P, we already have learned that. We know that the Bernoulli distribution or Bernoulli process, we divide the overall event into small intervals. Yeah, the overall event into small intervals with each, and every small interval is indicating an event, which we consider in two options. That is yes or no, which means P, Q with the probability P and Q, success or failure, go and no go, right? So, and we learned how to take mean, variance, right? We know how to take mean, variance. That's the easy part. Variance distribution function, probability function, probability mass function, and this distribution function. So all of these we have already learned in last lesson. Then we saw that how we convert Bernoulli into binomial distribution, right? Just by considering the n-independent Bernoulli random variables, right? If we sum that, it will be the binomial distribution. So if we sum n Bernoulli distribution, that is this one, it becomes binomial distribution. Here we have a limit of n. Then we have solved, and we also know how to get the parameters. So who can tell me what are the parameters of binomial distribution? In Bernoulli distribution, the parameters are 0 and 1, right? So what are the parameters of binomial distribution? Do you remember? Does anybody remember? Does anyone remember the parameter of a binomial distribution? What are the parameters of a normal distribution? A binomial distribution? No? No one remember? NP. N and P. Right? So we have also discussed some questions regarding binomial distribution. Yeah, so that's what we have gathered, like the probability of so probability function and the function of a binomial distribution, that is NCRX and P power X, Q power N minus X, which is Q power 1 minus P power N minus X. So this is a success, power X, and failure, power m minus x, and this is a combination. How we define the combination? Simple. It's n factorial divided by x factorial and n minus x factorial. Right, so that's how we calculate NCX. So what does that mean, NCX? That how many possible ways of drawing X from N population. We will also see examples in today's lesson. Right, so, oops, what happened? So that was about the binomial distribution, right? So we know that through the parameters n and p, what shape our distribution, binomial distribution can have, and it can have different distribution. Remember, as the n tends to infinity, the binomial distribution tends to become normal distribution, right? So we have done some examples, so I'm just keeping the examples. And then today we will talk about another form of a discrete probability distribution. What is that? That's known as Poisson distribution. What is Poisson distribution? So in Poisson distribution, the parameter is lambda, right? So that's the parameter. So here parameter is lambda. We know that in binomial the parameter is NP. In Bernoulli the parameter is 0, 1. Yeah, and in Poisson the parameter is lambda. How to define this lambda? Let's see. But first, let's see the probability function in Poisson distribution. I'm not getting into the proof of this, but there is certainly a proof. We will see different proof of in hypergeometric function. But here, probability function is given as lambda power x e power minus lambda upon x factorial. Yeah. So x is like 0 to n. So we consider it a lambda, or you can also say mu, because it's an average. That means we consider it as a rate, right? So what is lambda? Lambda or mu? So lambda is, you can also consider it as a mu or an average. That means, so I can say it's an average. It's an average or a rate. Right? What kind of a rate? Like mean number of occurrence in the interval, and this interval is fixed. So again, here we can draw an interval from certain interval which is fixed, right? So as remember one more thing here, that if we exemplify the lambda, what kind of example we can get? For example, lambda can be a number of an event out of an interval. What's that? That can be, if we exemplify, can you give me an example for lambda? I can give you an example of lambda. You can think about that. As I told you, lambda is an occurrence in the interval, and this interval is fixed. So I say, if I want to exemplify, can I say that lambda is a number of calls per hour? Now, number of calls per hour, that's fixed, right? Hour is fixed. So this interval is fixed. That's 1 hour. Similarly, you can say number of accidents happened on the street per day, or day 1. And so all of these are the ratios, these are the rates. Some fixed from some fixed interval, you get the ratio. You get the ratio of some occurrence in a fixed interval. Do you understand? So parameter of a Poisson distribution is equal to lambda as well. And obviously we have discussed that parameter of distribution defines the shape of the distribution. So as the lambda increases, the shape becomes symmetrical. Shapes become normal, right? See, if lambda is 1, lambda is 2, it's getting symmetrical, and lambda is 5, it becomes symmetrical. It means normal. So, but and as we get lambda smaller and smaller, the shape moves from the positive skewed. So distribution shapes depends on the parameter. And second important thing is the range. What is the range? Here, which means that what can be possible value of a random variable. So range of a Poisson distribution is up till infinity. So you can have 0, 1, 2, 3, and so on, infinity. That's the range. 0, 1, 2, 3, so on infinity. There's a range, and parameter is lambda. And we know that what is lambda? Lambda is number of calls per hour, or number of accidents per hour. So it's an occurrence of an interval or occurrence of an event from a fixed interval, and that's the probability distribution. In this formula, you can see E is a Euler's constant, and which is approximately 2.7. So if lambda is given, x is given, you can easily find the probability. For example, probability of x equals 2 can be, and lambda is, let's say, 3. That's lambda. Oops, that's too much. Okay. Probability of x equal to 3 and lambda is 2. And just to put the value in here, and you can get 3 power x is 2, and times E means 2.71 power minus 3 divided by 3 times 2 times 1. So solve it and you get the probability of x equal to 3. And you can also use the probability. For example, let's say n is like you have the fixed interval, and you can have like 5. Probability of x is less than or greater than equal to. Why it's happening like this? Actually, let me talk on the board. So now if we will have to find probability of x equal to 3, whereas lambda equal to 2. So in this case, what is the probability of x is less than 3. Greater than equal to 3, and n is let's say 25. So in this case, it will be hard to get probability of x is greater than 3. So what we have to do, we have to put complementary law, that is 1 minus probability of x is less than 3. Right, so it will also give me the same answer. So you often have to use complementary law, as in this case where it's really high number of values you have to calculate. You just simply because here n is 25, so you just simply use the complementary law and subtract it from the 1 and the remaining of the probabilities, and you can get the same probability. So in this case, 1 minus probability of x equal to 0 minus probability of x equal to 1 and minus probability of x equal to 2. Alright, so that's how you get, and here it's like in each of this you have to put this formula of probability of in Poisson distribution, and that's the formula is e power minus lambda power x upon x factorial. So here you can put 0, 1, and 2 in this equation, and you have the value of lambda and e. So that's how you continue. Is it clear? How to remove all of it? Anyway, so let's go to slides again. Now, here in Poisson distribution, we know the range is 0 to infinity, the parameter is lambda, and the mean is lambda. That's the thing here. So mean is equal to variance. So mean is lambda and variance is lambda as well, because it's fixed interval, right? That's why the variance is the same fixed error. Why it changes over this again and again. So now we can also use binomial distribution along with Poisson distribution, which is known as Poisson approximation to binomial. We will see the Poisson approximation to binomial. That how through binomial we get the Poisson distribution, right? But before that, let's discuss Poisson process. So in Poisson process, what we have to do, we have to include the time, right? We assume that lambda is in a fixed interval. We know that. So what we do, if lambda is varying over time, so we have to add t. So this lambda is varying over the time. Yeah, usually it's fixed, but if it's vary over the time, then we have to put t. So how we can do that this time? So it will be the new p of x will be probability of x equals small x, lambda, because now we are talking about time, so xt. Sorry, so by including time, we get probability of x equals small x equal lambda e power minus lambda t, and remaining is same time. So this is t. Oh, I cannot write in this way. Let me write here. So probability of x equals small x, and here we have e power minus lambda t times lambda power x upon x pictorial. Do you understand? So here we get t with the lambda, because now we divided, because lambda is varying over time, so we have to add t. In Poisson process, the parameter is not only lambda, but lambda t. So parameter from lambda, it becomes lambda t, where t can be time. This t can be time. Mostly it's time. You can also say it's a space, or it can be any length or area, right? Or area. So for example, again, when we talk about time, so in a certain time, how many calls you receive, or in a certain day, on a certain day, how many accidents happen. So those number of accidents can change, can vary, right? Whereas in length, you can say an example that I'm producing textile, the clothes, and I can say that in 1 meter of clothes, the machine is producing how many defects, how many flaws. We'll see the example of this as well. So that's how we define Poisson distribution with time. Now, so let's move ahead. So how we do that? We know about the time homogeneity, probability of k arrivals in interval of distribution duration t, right? So we can have this time over the period 0 to t, right? This 0 to t. We divide this time into t into sub events, right? When we were talking about Bernoulli, delta shows a very small probability, right? This delta shows a very small probability when we were talking about the Bernoulli. We can further divide t into t1, t2, t3, and so on in the subdivisions of equals to delta. So first we divide the whole time in t1, t2, t3, and then we divide all. So together, if you see, it gives us the Bernoulli look, right? If we don't consider t1, t2, t3, t4, right? Because everyone has a space of a delta. That's the really, what is delta? Delta is the really smallest probability. So we divide the whole time into different time intervals, and then we further divide t1 into delta, t2 into delta, where delta is the possible smallest probability. We do that because, as I told you, we can also solve binomial into Poisson distribution. This means we are approximating Bernoulli process to convert into a Poisson process. In other words, since we can convert Poisson into Bernoulli, how we do that? We have like this is usually the Bernoulli. It's almost like similar to Bernoulli probability distribution. If we consider that if certain event happens, then if the probability is 1, if it doesn't happen, then 1 minus p, which means q, is 0. And if it's greater than 1, if it's otherwise it's 0 if it's greater than 1 or less than 0. That's same as a Bernoulli process. Let's first take, now we are going to use this and approximate into Poisson process. First divide the into for a smaller portion. Now we know that I divide t1 into n different time. So t here, right? What is t? T can be n times delta. In binomial we have n, right? We have time, we divide the time up till n, right? In Bernoulli we just divide into small unit, which is delta. In binomial we divide up till n. So can I say this whole t, this one t, this is like n times delta, because we subdivide this into delta, delta, delta up till this point, and which is n, right? So every small t, t1, t2, t3, it can be n times delta. Can I say that? Yes, of course I can say that. It means number of trials becomes what will be the n? So n will become t by delta. So we can again prove this in different ways. So here this is t and this is delta. Each space is delta, and this t is actually this one, and similarly this one is this one. So now we got the n, right? So probability of success here, what is probability of success? It's p. And what is p? That is, so what is p? That is delta, lambda delta, right? Because we know here it's lambda, and we got that p is a success, and it's given as lambda times delta, right? So what is delta? You can say it's lambda, and delta can be t by n, right? So by putting the value, we can get Bernoulli, and it's p. In simple way, we know that the mean in binomial distribution, let's take it through the binomial distribution. What's the mean of the binomial distribution? So the mean of binomial distribution, I'm just gonna use this one, right? So what is the mean? So in binomial distribution, the mean is NP, right? And in Poisson distribution, the mean is lambda, right? That's we know. That's a Poisson distribution. That's a binomial distribution. Now we are dealing with the Poisson distribution, and we have here time t. That's t, right? So NP, both mean are equal. So NP becomes lambda t, right? And from here you can again get the p, which is lambda t upon n, right? That's the p. Now you know what is q. Q is 1 minus p. So you can solve it q as 1 minus lambda t upon n, and you can get q. But you see this p is same as this one. So through this you can also get probability of success. Now do you understand this? So we use n and p, and we define a binomial distribution. Now here I'm talking about that p of a k arrivals. Now that's the event. So it will be given as n combination of k, means how many ways k can be drawn from total n. And of course p. Now this is a binomial distribution, right? So if you remember, we have done ncx p power x q power n minus x. That's a binomial. But just instead of here, we just put the probability of p and q of for Poisson distribution. So we have nk lambda t, and just putting the values. Just putting the value of p and q into this equation, and we get this one. So now as the minimum, the delta will be, or n can be infinity, then it tends to the binomial. Delta tends to 0 means there is a very, very small probability. If the probability of success is very small and n tends to infinity, then this tends to 1. And this tends to 1, and this tends to e minus lambda. And here you can get the probability of k arrival in time t fixed into lambda t power k. We are using Poisson distribution for k is 0, 1, 2, and that's how you can make a Poisson table of a Poisson distribution. Do you understand this? So after solving this mathematically, at the end we approximately convert Bernoulli into a Poisson process, because this is a Poisson process. So here we can also get the mean for Poisson is lambda t, variance of Poisson is lambda t. Yeah, do you understand? Do you understand that? If you do, let's solve the question. Now here we have a question. It is known that 5% of the books bound at a certain, that's p, simple, at a certain binary have defective bindings. Find the probability that 2 of 100 bricks. Now this is interval, total n is 100, and you have to find p of x equals to 2. You have to change the Poisson approximation to the binomial distribution, right? So how are we going to do that? Simple. Now, what is p? We remember we use approximation when n tends to infinity, right? And or p is very small. I mean, probability tends to very small, right? Means p tends to 0. If this is the case, then we use the approximation, but theoretically speaking. But here in this example, what is p? 0.05. It's small, but not that small. And what is n? It's 100, but not that. It's big, but not that big. So what is the probability of x equal to 2? We know that here lambda equals np. We just have done this. So what is lambda? You can get the value of lambda, which is 100 times 0.05, which is 5. Now this is lambda. Remember, in Poisson distribution, variance and means both are lambda, right? At this moment, we didn't include time, right? So simple. What will be the probability of x equal to 2? E power minus lambda, which is minus 5, 5 power x, lambda power x, which is 2 upon x factorial, which is 2 factorial. Now, if you put the value of 2.7, right, 2.7 and minus 5 and 5 square 25 times 25 divided by 2, you can solve it and you can find, let's say it's 19.4% or 0.194. Example, it's not exactly 0.194, but you can solve it. So it means there is a 19.4% chances possibility that our x is 2, that the book is defective, right? So 19% chances. Now let's take another example before we go on a break. What is this example? You have a heavy machinery manufacturer that has 3,840 large generators to produce in the field that are under warranty. Now here n is really big, 3,840. If the probability is 1 by 1200, it's very small probability. So for sure, it's a question of a Poisson approximation. Right, so it's a question of a Poisson approximation because n is really high and p is really small, because that's what we dealt with, that anyone will fail during the given year. Find the probability that at least 4 of the generator will fail during the year. So here in this case, what will we do? What is the probability? N is given. What is n? 3,840. P is given 1 by 1200, right? And you have to calculate probability of x is greater than equals to 4. Now it's really hard to calculate because n is 3,840 and you have to calculate from 4, 5, 6, 7 and up to 3,840, which will be very, very difficult and hard if you calculate it manually, even through Excel or some other software. But what you can do, you can simply apply the complementary law. That is, it should be equal to 1, because we know the sum is 1 minus probability of x less than 4. And then you can find out different probability. X equal to 0, probability of x equal 1, probability of x equal to 2, and probability of x equal to 3. So what is probability of x equal to 0? You know that lambda is np, so you just multiply this n with this p, and it can give you 1 by 12, 1 divided by 1200. So that's the probability. I multiply by 3840, 3.2, right? So NP is lambda is 3.2. I just multiply NP. So NP is 3.2. So lambda is 3.2. So what is E? E, you know, E power minus 3.2. And here lambda is 3.2. Power x is 0. And below is 0 factor, which is 0. And then it's e power minus 3.2, 3.2 power 1 divided by 1 factorial, and this and this and this, and then at the end you can add all of these probabilities, and 1 minus this can be this. So you can solve it at home later on, right? So let's take another example before we can have a break in a few minutes. Don't worry about the break, but let's finish the Poisson as well. Now this is really important because here the time is involved. So far there was no time, and we know that when time is involved, what is the probability? So probability of x equal to small x when the time is involved, then it's e minus lambda t, yeah, and then lambda t power x upon x factorial. That's the when time is involved. Now here, suppose the flaws, which means crack, tips, specks, occurs on the surface of a glass with density of 3 per square meter. So what is 3? That's our lambda, right? What is the probability of there being exactly 4? We have to calculate probability of x equal to 4. And on a sheet of a glass of area 0.5 square meter. So this is the length given. So of course this is the time, t. Yeah. So how to do that? Simple. You have lambda equal 3. You have time equal 0.5. And you can have find x equal to 4. Now it's easy for you to put the value of 3 and 0.5 here. So 3 times 0.5 is lambda t, which is 1.5, right? So e power minus 1.5 and 1.5 power x is 4 divided by 4 factorial. So that's how you use Poisson distribution and you get the value. So what does this mean? So if it's let's say 23.0.234, so it means 23.4%. I'm talking about the solution of this. I'm not exactly sure, but if let's suppose that if this is the thing, so we can say that 23.4% are the chances of having 4 flaws in 0.5 square meter. So I repeat, how can we interpret the result? There are 23.4% chances of having 4 flaws in exactly 4 flaws in area of a 0.5 square meter. So that's how we deal with exactly that's how we deal with Poisson distribution. Now you know the parameter of a Poisson distribution, um, how we calculate the probability function of the Poisson distribution, and how we change from Bernoulli to a Poisson distribution, right? So let's take a break here. Do you understand? Is it clear? Do you understand the concept of Poisson distribution? Do you understand the Poisson distribution? Okay, so let's take a 10 minutes break and then we can do the last distribution of a discrete probability distribution, and that's hypergeometric distribution. It's easier than the Poisson. So now you know Bernoulli, now you know binomial, and now you know Poisson. So let's take a 10 minutes break.